Okay, everybody, I'm going to get started. Today we're going to talk about these two topics, partial measurements and this so-called spooky action at a distance. It won't get too spooky. It'll get a little more spooky next time, but we'll start in on it today. I want to just recap a little bit what we did at the very end of last lecture because it'll lead in a little bit to what we'll do when we talk about partial measurements. So we were studying multi-qubit systems last time, or multi-particle systems. And let's remember, let's say Alice prepares a single qubit like a photon, so it has some two-dimensional state, alpha 0, alpha 1 are the amplitudes. Similarly, Bob, another qubit, phi. And then they're going to maybe make them, do some physical interactions together. So they get them ready. This is my picture of two particles. And this is them, I don't know, flying off to the device that they're going to enter. So let's first recall, what is their joint state here when they just came together and they're quote-unquote unentangled. The joint state is given by the tensor product or Kronecker product, psi tensor phi, which is this four-dimensional thing with all the pairwise products of amplitudes. Okay, and then perhaps they may go into some, this is just a hypothetical example, two qubit gates or physical devices that operate on two qubits or particles simultaneously, that's a C0 gate. Or maybe they'll go through a swap gate, which is another two qubit gate that I think I've mentioned before. Okay, or some other things. And these are all represented by 4x4 unitaries. And you get the resulting state here by multiplying the incoming state by the appropriate unitary matrix. So let's say the state here is something. I'll just call it xi. I think that's a xi, which is a unit vector in 4 dimensions. And by the way, just as a reminder, what is psi or xi? Well, you get it by starting with this state, psi tensored with phi. And then the first thing you do is in this picture is apply C0. So this is a 4x4 matrix, and this is a length 4 vector. And then the second thing you do in this picture is apply swap, which is the product with another 4x4 matrix. And I write this down only to make this annoying point that it's visually the opposite of what you see here, right? So if you draw the diagram like this, where first they do C0 and then swap, when you actually write the matrix product, it's C0 is on the inside and then swap is back here. It's unfortunate that people that started this did not originally assume that all the state vectors were row vectors and they multiplied from the left. Then it would have been perfect. But anyway, so we have this slightly backwards thing happening. OK, so that's fine. But then the main thing that we talked about last time in the second half of last lecture is, what happens if now Alice applies some 2x2 unitary to her particle? Seems like a little bit of a tight mismatch. If she passes it through, I don't know, some Hadamard gate or a NOT gate or some 2x2 operator U, what happens? Well, as we saw or calculated or we learned, the state at this point is U tensor product or Kronecker product with the 2x2 identity matrix applied to xi. OK? And the reason the identity matrix shows up here is because you could sort of imagine that as you were applying U on the first qubit, you were doing nothing on the second qubit. OK, so you could have drawn the diagram like this, where nothing happens to the first qubit. This is the identity matrix, which does nothing. OK, and then this is a 4x4 unitary transformation. And so you can just naturally multiply it against xi. OK, and then if, hypothetically, things went on, and then Bob did some 2x2 unitary v to his qubit, then what would the state be here? The state would be, well, now we've done I tensor v to the previous state, which was U tensor I times xi. That would be the new state. And one thing that we sort of saw or checked last time is that this is equal to, by, let's say, the laws of linear algebra, if you go to the definitions, U tensor V applied to psi. And so in particular, what that means is, you can kind of tell, you would get the same final state had you done V here before, in time, you did U. So if I move this V to here, so I did this first, well, you would do the same calculations. These would be reversed. But the way this multiplication works, you just multiply the components. And you would still get U tensor V applied to psi. And in fact, the most common thing people will draw is just we'll draw them happening at the same time. I don't know, it saves horizontal space. And so you can think of like U and V together as turning into this. OK, so like the thing to take away from this is that like if you do unitary transformations to separate particles, then it doesn't really matter in what order you do them. You'll get the same result. Okay. And even just to quickly remind you why that is, it's sort of clear if you had done this to unentangled particles. Like say, Alice and Bob prepare two particles both in the state U, and they're unentangled. And then they just immediately do this thing of like, OK, first Alice applies U, and then Bob applies V. I mean, what is the state at this point? I mean, nothing even got involved with Bob's qubit. So I mean, the state of the qubit here is fairly described as U applied to 0. That's fine. This is a 2×2 matrix. That's a length 2 vector. OK, and then this new particle in state 0 joins the party. So the state looks like this. And then here, like V gets applied to this particle. And again, actually, Alice and Bob didn't even need to be together in order to do this. They could have done this sort of separately, independently. So it's sort of clear that at this point, the state is U applied to 0, tensor with U applied to V. Sorry, V applied to 0. OK, which is the definition of U tensor V applied to 0, 0. And then you can make the same reasoning as if this were 0 and 1, 1 and 0, and 1 and 1. In all four of these unentangled cases, you'll just get the same calculation. You'll have the four possibilities 0, 0, 0, 1, 1, 0, and 1, 1 here. And then you've reasoned yourself into knowing like where this operation, this bigger operation, sends each of the four basis vectors in 4 dimensions. And then since it's a linear transformation, like once you know what it does to basis vectors, it follows what it does to every vector. OK, so that's just sort of a little bit of a justification for why the rules work like they do. But if you want to forget that, you can just take all of this on faith. That's just the simple linear algebra of how it works. So one reason I wanted to recap that is to say that this property that if you sort of do unitary transformations to separate particles or separate qubits, then it doesn't matter in which order you do them. This also holds equally well, as it turns out, for measurements, which are kind of the other thing you can do to particles in the world of quantum mechanics. You can do these unitary transformations, which are just linear transformations on the state. And you can do these measurements, which have this kind of funny property, like they have a readout, which is some classical information, and they change the state, and so forth. But it'll turn out that they share this property, that if you do them to different particles, it doesn't matter what order you do them in. So let me explain that, and I'll in fact have to explain to you like what is the rule for what happens if you have some entangled particles and you put just one of them into a measurement device. OK, so let's assume basically the same setup, but to make it slightly more vivid, let's imagine we really have two photons. And we care about their polarization. So I mean, we designate one of them as belonging to Alice, and one of them is belonging to Bob. OK, and one thing that we know is OK, they have some joint state, which is a 4-dimensional vector, and we just had this law about what happens when you measure a d-dimensional state. You have some readout, which is one of d possibilities, and then the resulting state snaps to or collapses to the read out possibility. So let's say that they start in some potentially entangled state here. So let's say their state completely generally is alpha 0, 0, amplitude on 0, 0, and similarly. Okay, and we know that if you pass this, the 2 photons in this state through this device, then it'll, this readout will say 0, 0 with probability magnitude of this squared, and it'll say 0, 1 with probability magnitude of this amplitude squared, and so forth. Okay, so that's the rule for measuring one system. And you can build such a measuring device in real life, but we're probably more used to, I mean, we spent the first few lectures talking about like the simpler scenario where you just measure one of the photons. Like these polarizing lenses were kind of like measuring devices. So like what happens if you just take these 2 photons and pass one of them through like a polarizing lens? I mean, something's got to happen, so let's learn what happens. And just like last time, what happens is like, I think the most logical thing, like the thing that you would guess, if like I made you guess like what happens. And it's very much, again, also like what you would get if you like made the analogy to probabilistic computing and thought about this as like conditioning on one of 2 different random variables. Okay, so yeah, let me scratch out this picture and try to ask what happens if we just put this into like a 1 photon measuring device. So we have to answer 2 things, like what will go on with the readouts, and then like what also will be the state of the 2 photons that come out. I mean, not come out, but the 2 photons here. All right, well, I'll just tell you the answer. Okay, so the probability that Alice's measuring device will read out 0. Okay, this is a measuring device that, it's got some LED screen that spits out either 0 or 1. What's the probability that it reads out 0? I'll just tell you, it's the sum of these magnitudes, alpha 0, 1 squared plus alpha 0, 0 squared plus alpha 0, 1 squared. Okay? That's definitely a non-negative number. It's between 0 and 1, so this makes some sense. It's possible. And in general, what's the overall rule? I picked out the amplitudes that were next to basis states, which were like consistent with the readout I'm talking about, right? I mean, these basis states, the first symbol refers to Alice's qubits. So I picked out all the ones where Alice's qubit had a 0 in the name of the basis state, which is this one and I took the squares of the magnitudes of those amplitudes. So that's the general rule. I'll illustrate it in more general cases in a minute. But that's the probability of this event. And then, as with measuring, right, if this event occurs, it collapses or like changes the state. But we have 2 particles hanging around, so we have to understand what the joint state of them collapses to. And I'll just tell you. And if it occurs, the joint state, becomes, well, I'll first write down something that's like mostly right, but a little bit wrong. It becomes this, alpha 0, 0, 0, 0, plus alpha 0, 1, 0, 1. Okay, and what I did here was, again, I just selected the piece of this joint state that was consistent with the measurement outcome, i.e. that had a 0 in the first position. Okay, so what is the thing that's kind of wrong about this? Yeah. The squared magnitudes don't sum to 1, right? I mean, this is a 4-dimensional vector with coordinates, alpha 0, 0, alpha 0, 1, 0, and 0. But state has to be a unit vector. The sum of the squares of the unit vectors has to be 1. So far this looks like nonsense. The truth is just that like the most simple way in which it could be a unit vector is what happens. So like it becomes this divided by square root of a number p0, which I'll just define to be this. Okay? This is not like usual notation, but I just didn't want to write so many symbols. the state becomes this, where P0 is this quantity. Okay? And now this is like sensible because, this is the, let me write it again. This state can also be written like this, alpha 0, 0 over root, well, I'll write the whole thing. Alpha 0, 0 squared plus alpha 0, 1 squared. That's the first coordinate of the vector. The second coordinate is alpha 0, 1 over the same thing. And then the third coordinate is 0, and the fourth coordinate is 0. And what do you get if you square these magnitudes and add them up? You get 1, right? Let me not write it, but magnitude squares sum to 1. Good. And that's it. That's the rule. Well, I've only done half of the cases, but let me write out the other case. So with probability this much, which I called P0, the machine has a readout of P1. And the other possibility is that the measuring device reads out 1. Those are the only two things that can happen. So like it kind of must be the case that this is 1 minus P0, because how could it be otherwise? But in particular, this is also can be achieved by sort of following the same rule. In other words, it's alpha 1, 0 magnitude squared plus alpha 1, 1 magnitude squared. Where here what I did was I took all the basis states that were consistent with Alice having 1, which are the 1, 0, and 1. I took out the amplitudes, I squared them, and summed them up. Okay? And if this happens, the new state is same thing. You just retain the piece that's consistent with what the measurement outcome was, and then it's called normalize it so that it's actually a unit vector, a state vector. Okay, where here I just invented the notation P1 for this. Okay. Any questions? Let me add a remark. Take a look at the state that comes out in each of the two possibilities. Is this state entangled or unentangled? Can you tell? Yeah. Yeah, in both cases, it's unentangled. I will write that. Okay, remember, unentangled means it can be written as a tensor product. So like, e.g. in the readout 0 case, okay, maybe it's not super clear, but this is the state. And if you think about it, it's 0 tensored with alpha 0, 0 over root P 0, 0 plus alpha 0, 1 over root P 0, 1. Let me just multiply this out, you get this. Okay, so it becomes unentangled. And that's sort of kind of maybe nice and reassuring. Like it kind of means it's gone back to a situation where, Alice's qubit can really said to be in this state 0, and she could take it away, walk away. And you can fairly say that her state is 0 and that Bob's state is this. Okay. Okay, now I want to talk about a mathematical kind of subtlety, which is, let's say we do exactly this experiment. And in some sense, I just told you what happened. I'm going to erase some of this. But suppose I want to say, this is a kind of a subtlety to do with a topic called mixed states. Suppose I just said, You said, remind me again, like what is the state of the two particles in the broad sense? What's going on with these two particles after this operation? Well, this state, the correct way to define it is that it's a classical probability distribution over quantum states. Now, actually, if you physically do this experiment, then, one of two things will happen. Like 50% of the time, it'll read out 1, and then you can just say, yeah, the state of the particles at that time is this, the end. But if you kind of would say, like, well, I haven't done the experiment yet, but like I'm going to mathematically model this, like what is the correct way to model mathematically what's going on here? The correct way to model it mathematically is like you have a probability distribution over quantum states. And this kind of object comes up a lot eventually in the study of quantum mechanics and quantum computing. It's called a mixed state. And these kind of things, the things that so far we've been calling quantum states that look like just this, like a superposition over basic states, these things are called pure states, a pure quantum state. And it's a little bit like this analogy. If you ever studied like game theory, like the distinction between like pure strategies and mixed strategies, that's a little aside if you ever did that. It's the same thing here. Like, the thing that we had normally thought of as a quantum state is called a pure quantum state. And then sometimes you might be analyzing a probability distribution over pure quantum states. So this kind of object is a little bit confusing, right? I mean, we just got here. We just started some quantum states. Like, I don't want to say, like, and now, like, consider the further generalization where you have a probability distribution over linear superpositions of, basic states. It's a little bit confusing. So, we want to, like, mainly study pure quantum states. Eventually, like a dozen lectures from now, we'll start studying like mixed quantum states because there is a sense in which like that's the true state of like a quantum particle. Like the best mathematical way to describe what is the state of some particle is via a mixed state. But I don't want to get too complicated yet. So we're going to mostly focus on pure states for a while, as we like to do. And because of that, like all of our experiments, our diagrams, like the quantum computing diagrams, we'll mostly only have like measurements at the very end, right? Because if you have like a measurement in the middle, then you kind of get into a situation where you have a probability distribution of what's going on, and it's like very annoying to like carry all that through to the end. So we want to just mostly work with pure states all the way through, and maybe at the very end we'll do measurements which introduce classical probabilities into the picture. Yep?
Are there cases in real applications where you want to measure in the middle to do stuff like that?
Yes, there are cases where it's effective to measure in the middle, and it can lead to, like, let's say, for example, the most effective way, if I understand correctly, to do the quantum Fourier transform, which is a major thing to talk about, does involve like doing measurements in the middle. And if you do that, it makes the whole circuit for it simpler. Let's say in practice, like because you have to use fewer like 2-qubit gates than you did if you don't want to use measurements in the middle. But as we'll see, like for the purpose of quantum computation, you can sort of, without loss of generality, move all your measurements to the end and sort of thereby only work with pure states throughout. And so it becomes mathematically more simple. And so that's what we're going to do, and that's what most people do. They almost don't exclusively talk about like just good old pure quantum states throughout, and only get into mixed states when it becomes sophisticated, and you need to do that. However, since we are talking about these things, I'm actually going to talk about mixed states a little bit in this very lecture. Okay, so right. So in fact, the actual mathematical description of the 2 qubits state at this point, if we don't actually do the experiment and like see which way it turned out, if we just want to analyze it overall, the actual state, mixed state at question mark is 50%, sorry, not 50% chance, p0 chance of this thing, alpha 0, 0 over root p0, 0, 0 plus alpha 0, 1 over root p 0, 0, 1 and p1 chance of this. Okay. Okay. And okay, I do this. I write this all down because now I want to imagine. Okay, well, what would happen if now we put Bob's qubit into a 1-bit measurer? Okay, and we can do this. Like we first use classical probability to say like, okay, well, there's a p0 chance that the situation will be here, and then we'll do the 1-qubit measurement rule that I just told you on this object. And there's a p1 chance that it's here. We'll do the 1-qubit measurement rule I just told you on this object, and we'll see what happens. Okay, so right, so we've gotten here. Now some probabilities have been introduced in the world. Now we're measuring the second qubit. Okay, so it's kind of like we say, case 1, well, I should call it case 0, which is this case. Okay, with p0 chance, the state is this. And now what happens when Bob reads his particle or measures his particle? The probability that Bob's readout is quote unquote 0 is, well, remember the rule, you look at all the components of the state that are consistent with Bob's qubit being 0, which is just this one actually, and you square those magnitudes. Okay, so it's simply alpha 0, 0 over root p0 squared. Okay, which is the magnitude of alpha 0, 0 squared over p0. And if so, the state changes to, okay, what do? You retain all the pieces that are consistent with it, which is actually just this one. And you divide by the square root of this probability in order to make it a proper state. And what happens? Well, I mean, there is only one coefficient here. So when you divide by the square root of its square, it just cancels itself out. And the state changes to just 0, 0. Okay. And what about had Alice's readout been 1, this refers to Alice's readout. Had Alice's readout been 1, this would have been the state going into Bob's measurement. So again, we pick off all of the, well, let me write it. The probability that B's readout is 0 in this case. We pick out all the pieces here consistent with Bob's readout being, or qubit being 0, which is just this piece. Okay, so it'll be magnitude of alpha 1, 0 over root p1 squared, which is alpha 1, 0 squared over p1. Okay, and in this case, the state becomes just 0, 1.
Okay.
Yeah.
Are we working with real amplitudes?
No, complex amplitudes.
I mean, then the state might be not 0, 0, but something like unit vectors times 0, 0, 0, like unit complex amplitude times 0, 0, because if alpha 0, 0 is not we're only dividing it by its amplitude, right?
No, we divide by the square root of the square of its amplitude's magnitude. So like in this case, I mean, it's not written right, but what was p0? It was the probability that Alice would see the readout 0, which was magnitude of alpha 0, 0 squared plus magnitude of alpha 0, 1 squared. And we divide, that's a real number, and we divide by, the rule is that you divide by the square root of that real number, which is a positive real number.
But you divide by complex number.
Yeah, but alpha 0, 0 is complex number, which we divide by
Yeah. Right. You're right. Good point. So you're saying this would actually become alpha 0, 0 over magnitude of alpha 0, 0. Okay, good point. Yes. Thank you. And this would become alpha 0, 1 over magnitude of alpha 0, 1. Good point. So in fact, even had I been assuming that the states are, the amplitudes are real, this would be either 1 or minus 1. Okay, and since they can in general be complex, this will be a complex number of magnitude 1. Good. So I'll say this again in a moment, but it's something I haven't yet said in this class, but I will say, which is that if you take a quantum state, like a normal pure quantum state, and like multiply it by -1, so you negate all the amplitudes, the resulting quantum state is like indistinguishable from the original state. There's no measurement or experiment that you can do that can tell the difference between them. And similarly, if you take a quantum state and multiply it by a complex phase, a complex number of magnitude 1, there's a sense in which you get the same state because there's no physical experiment you can do that will distinguish between them. Maybe I'll emphasize that again in a moment, but basically, you should consider psi and minus psi to be functionally the same state, and also I times psi. These are all sort of functionally the same states. In fact, there will be a homework problem, which is coming out today, by the way, about just this thing. Okay. So I guess you'll get more used to that after the homework, but you should mentally imagine that perhaps this is just the same as 0, 0. It would be true if alpha 0, 0 were a positive real number. Yeah?
Does this actually make sense, implies that in practice, you can imagine that all of these amplitudes are positive real numbers?
I guess not, because if you have a list of complex numbers, it's not necessarily the case that you can simultaneously make all of them real by multiplying by a complex number of magnitude 1. Right? If you have a state with one positive amplitude and one negative amplitude, maybe they're both real. It's true that if you just multiply the whole state by -1, it's functionally the same state, but you'll still have one positive and one negative. You can't make them both positive simultaneously. And similarly, you can't if you have a bunch of complex numbers, you can't make them all real simultaneously. Yeah. Good. So this is a bit of a subtle point, which actually I slightly wish you hadn't noticed because it would have made the exposition easier, but this is the truth of the matter. And it'll actually get to a good point, which we're going to stress later in the lecture anyway, that sometimes you have two states that look distinct, but actually they're sort of the same state because there's no operation you can do that will distinguish them. Okay, that may have been a little bit confusing. If it was a little bit confusing, then, well, you'll get used to it after the homework, and we'll come back to it later. But it was a good point. And let me now come back to the calculation I was doing. We'd sort of done 50% of the calculation. We saw that when Alice measured her qubit, there was a p0 chance you would get this into this state, and she would read out 0. There's a p1 chance she'd read out 1 and get into this state. And then in both these possibilities, we looked at the chance that Bob would read out 0. Okay. Okay. So now we can, for example, say, what is the overall chance that the readouts will both be 0? Probability that both readouts are 0. Well, this is now just a normal probability calculation. It's the probability that Alice is 0, and then it's the conditional probability that Bob's is 0. Okay? But what is that? That's p0 times magnitude of alpha 0, 0 squared over p0, which is magnitude of alpha 0, 0 squared. And that's exactly what, let me just write it like this. The probability that the readouts give 0, 0. That's exactly the probability that you should see 0, 0 if you use this joint measurement device. Right? And also the probability that both, well, that the readouts are, let's say, 1, 0. Well, for that to happen, Alice has to read out 1, which is a p1 chance. And then conditional on that, Bob has to read out 0, which is alpha 1, 0 squared over p1. So the total probability is magnitude of alpha 0 squared, which is, again, the probability that you would read out 1, 0 if you use this hypothetical joint measurement device. Okay, and I'll leave as an exercise for you to check the other two cases all work the same. Like the probability that the readouts are 0, 1 is alpha 0, 1 magnitude squared, and so forth. And furthermore, up to this little distinction about multiplying the state by a global phase, a global sign, or a complex number of magnitude 1, in this case, the state also collapses to 0, 0. And in this case, the state also collapses to just 1, 0. Okay? So what I'm saying is it acts exactly like the 2-qubit measuring device. So in summary, what this is shown is that, like, in some sense, this picture is like equivalent to, this picture, where you have like one giant 2-qubit measuring device. And it's also, you can imagine, again, I'll call it an exercise. You will again get the same picture if you had measured Bob's qubit first and Alice's qubit second. Okay, so just like when you apply 1 qubit unitary to Alice's qubit and 1 qubit unitary to Bob's. Okay, so that's reassuring. Okay, any questions? Okay, let me now say a subtle thing in words. Suppose Alice and Bob have a joint state. Okay? We just sort of decided that, okay, if Alice and Bob have their own separate particles, if they're just going to be putting them into their own little quantum machines, then you can treat them separately. But if they're going to bring their particles together and like jointly put them into a device, then you have to start keeping track of a joint state, like a 4-dimensional state. So let's say you do that, and now they have a joint entangled, 4-dimensional state. These are still 2 separate photons, and like it's possible for Alice to take her photon and say, "See you later, Bob," and like fly off to the moon, okay, or just like go far, far, far away, like never to be seen again, okay. And maybe like it's true that like in all the future, like Bob will never see Alice or her photon again, but like Bob's going to take his photon and start doing quantum experiments to it and so forth. See, like now that Alice is gone out of the picture, like you kind of feel like you wish to have like a 1-qubit description of Bob's photon, right? Like it should somehow, you would feel maybe have like some kind of 2-dimensional state, because it's itself just 1 qubit and like it's not going to interact with Alice or anything. But what qubit state does he have? So mathematically, it turns out you can, model the world in such a way that Bob has like just a state for his own qubit, if you promise it's never going to interact with Alice again. But that state is a mixed state. Okay, the correct way to model Bob's solitary photon is by a mixed state, and particularly that mixed state that you would get had Alice measured her bit. Okay, as we saw, like if you have this situation and Alice just measures her bit, like this was this part of the world, then the situation going on here, question mark, is like a probability distribution over unentangled qubit states. Right? You've got a probability distribution, like p0 of the time you're in some state that's of the form 0 tensored with something. This was with probability p0, and with probability p1 you got into this state that was like 1 tensored with something. This was like the mixed state at this point in time. And if Alice goes to the moon and we never see her again, you can like continue forth with your analysis by just saying, oh, the state of Bob's solitary qubit is this. It's p0 chance that it's this pure state, a p1 chance that it's this pure state. Okay, and you can go on and combine the usual laws of probability to deal with this with the laws of 1-qubit quantum mechanics that we know to deal with this. Okay? We're pretty much not going to do that for like the next dozen lectures because, as I said, like it's very annoying to like, on top of everything else, keep track of probability distributions on quantum states. Okay, but that is, mathematically how you can describe what goes on if you like take Alice's qubit away, never to be seen again. And it kind of makes sense. I said, it's what you get as if Alice had measured her qubit. Because in fact, if she goes to the moon and like Bob just walks around with his qubit and does something to it, how does he know maybe Alice did measure her qubit? Like maybe she did measure it on the moon, or maybe she is going to measure it in like 1 day or 1 week, like Bob doesn't know. And you'll find that because of this sort of exact property that like the measurements commute, it doesn't matter. If you keep track of Bob's state in this way, then like it doesn't matter if and when Alice measures her qubit. Okay. This is like a subtle point, which I wanted to say at this point, but I'll leave it at that. Any questions, though? I mean, it's a good time for a question. Yep.
So you're talking about entangled qubits, but in this example, they're not.
In this example, like if Alice really does measure, and it gets into the situation where, it's happened, and like it's definitely in one of these two pure states, then it is true that they're unentangled, and then like it's very unsurprising and fine for like, let's say this actually happens, to say that like, well, Alice has a qubit in state 0, Bob has a qubit in this state, and they're unentangled, and everything is very normal. If you simply haven't like literally done the experiment and you're just trying to mathematically model what could happen, then you have the only correct way to describe the situation here is by this mixed state. And then like maybe I don't want to get into like the definition of what does it mean for a mixed state to be entangled or not entangled, but let's suffice it to say, or let's call it entangled, because like you don't want to treat it as if they were unentangled at this point. Okay. Yeah, I want to give like just, to come off of subtleties for a moment here. Here I gave you the rules of what happens if you have 2 Q bits and you measure one of them. Okay. More generally, you could have like 5 Q trits, and you could measure the first, third, and fourth. And all the laws are what you would expect based on what I've said. In particular, for example, if you put the first, third, and fourth, Q bit or Q trit into like a 3 Q trit measuring device, it's the same as if you had put each of them individually into a 1 Q trit measuring device. But let me just, I'll give you like one example just to illustrate the general point. You can call this quantum mechanics law number 6 if you want. The rules of partial measurement. Okay, so let's say, I don't want to like introduce like, Alice has a D1 dimensional qubit and Bob has a D2 dimensional qubit. It'll be like too many symbols. So let's just say, to get the point across, Alice has a Q trit, a 3-dimensional state, and Bob also has one. But perhaps they've been through a lot together, so like now these 2 Q trits are entangled, so their state will in general look like, okay, alpha 1, 1 times 1, 1, plus alpha 1, 2, 1, 2, plus alpha 1, 3, 1, 3. Oops. Plus alpha 2, 1, 2, 1, plus dot, 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 plus alpha 3, 3, 3, 3. Okay? So it's a 9-dimensional vector. Okay, or we can write it like this. And then say, like, this first one stands for Alice's Q trit, which can be in basic state 1, 2, or 3. This one stands for Bob's Q trit, which can be in basic state 1, 2, or 3. And let's say Bob puts his single, 3 basic state particle, like a deuterium nucleus or whatever has this property, into a measuring device. So let's say Bob measures his Q trit. What is the rule of what happens? Well, again, Bob's Q trit measuring device has some kind of, readout. And it can show either the classical information 1, 2, or 3. So we need the probabilities of all these things. So like the probability is the rule that Bob's device reads out 1 is, again, you like take all the pieces that correspond to having a 1 in Bob's location, and you add their squared magnitude. So it's alpha 1, 1 magnitude squared plus alpha 2, 1 magnitude squared plus alpha 3, 1 magnitude squared. And if this happens, the state, quote unquote, collapses to or changes to, you just retain all these pieces, like all the vector pieces that are consistent. So that's alpha 1, 1 times 1, 1 plus alpha 2, 1 times 2, 1 plus alpha 3, 1 times 3, 1. This is still a 9-dimensional vector, but 6 of the components are 0. Or more if some of these alphas are 0. And well, this is not quite right because this is not a unit vector, so you have to divide all these by some number which will make it a unit vector. So I'll call that q1, square root q1, square root q1, where what is q1? It's this. Okay? And similarly, probability that Bob's device will read out 2 is magnitude of alpha 1, 2 squared plus magnitude of alpha 2, 2 squared plus magnitude of alpha 3, 2 squared, and so forth. Okay, and this is also, as we've said before, this is actually an unentangled quantum state because it's this. Oops. Etc. Okay, is it okay? Okay. So now at this point, you really, really know all the law. I mean, for sure now, you know all the laws of quantum mechanics you need to do quantum computing. Like, you really know it all now. Good, which means it's time for the spookiness. We're not going to get into the quantum computing yet. We're going to actually spend, some lectures thinking about all the, interesting things that can happen as a result of these laws of quantum mechanics. Quantum computing is sort of what interesting things can happen if you get together like 100 particles and do like a bunch of stuff. But there's lots of interesting experiments and cool things you can do even if you have like 2 qubits, If you just have like 1 qubit, like it's not very interesting. Nothing too much can happen. There's that Weidmann-Baum thing. That was pretty cool. Elitzur Weidmann-Baum. But it gets really exciting once you have entangled qubits. Okay? So let's get into this excitement. Good. Let's actually stay in this same scenario. Let's say Alice and Bob have 2 photons, and they do like that thing that quantum people love to do. They prepare an EPR pair, okay? Which is 2 qubits in a very particular, very interesting joint state, an entangled state. So say we have Alice and Bob, and they have their own photons, but these are in a joint state, which is the Bell state. That's kind of the AKA of an EPR pair, which is 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. Okay, so this is an entangled state. They can get it by, Alice. Well, they start their states in 0, 0, and Alice does a Hadamard to her qubit, and then they do a C0 to both their qubits. Okay, and one thing I want to emphasize is you can physically do this. They're pretty good at this now. I mean, they can get pairs of qubits into this state. And then you can really do the other thing, which is like you can take 1 qubit far away, and they can be very spatially separated, and yet still they have this joint state like this. Okay, so in fact, this is always like the start of cool quantum experiments. Like stage 1, like prepare like some Bell pair, some EPR pair. And for example, like one cool quantum experiment that they can do, which we're going to talk about in a couple lectures, is called quantum teleportation. It's a very fancy name for it. We'll see. It's pretty cool. But stage 1 of it is prepare this Bell state, and like they want to always do these like quantum teleportation experiments with the 2 parties like far apart, like literally in space, to make it particularly cool. And up until recently, like the coolest version had been done in 2012. In the Canary Islands. So like they got, this situation where like one of the particles was like in La Palma and the other one was in Tenerife, and these are like 2 islands that are 143 kilometers apart. And yeah, they were like jointly in this entangled state. But now, like it's even better. Like I think last year, Zhenwei Pan's group in China, like they set it up so that like one qubit was like in Nagari, Tibet, and like one was on this satellite called Mishus, like in space. And you know, the distance actually varies as time goes along, but it's like between 500 and 1400 kilometers. Okay, so they can really do this. They can get like these entangled qubits that are like super far apart, and then they do their quantum teleportation experiments. Yeah.
Can you entangle far away things, or do you need to bring them closer?
You need to bring them closer, yeah. So in order for them to get entangled, they have to be like physically interact with each other. Yeah. Okay, so yeah, so let's imagine that Alice takes, you know, they do this, and then Alex takes her qubit to the moon. Okay, and Bob stays on Earth. And okay, so let's say Alice on the moon. I should have drawn a picture, but I can't do that. So like on the moon, measures her qubit. Okay, so let's just, what happens? Okay, so well, we know what's the chance that she'll measure 0. It's, this is the only one consistent with it, so it's the square of this. So it's a 50% chance. So she has a 50% chance of, you know, measuring 0, say. Okay, so maybe that happens. She puts it in her measuring device, it's like 0. So then, what happens, according to these rules? Well, now, the joint state, assuming this happens, is 0, 0. Which you can maybe also write as 0 tensor 0. And so one can say that at this point, you know, Bob's state, Bob's qubit, is now in state 0. Like this is kind of a valid statement because these are unentangled, so you can really treat them separately. And it sort of happened like instantaneously, if you will. So for example, like when Alice does this, she's like, huh, 0, okay. She knows Bob's qubit is in the state 0. For example, she now knows that if Bob on Earth were to measure his qubit, he would definitely, 100% chance, get 0. And perhaps you think that's a little bit strange, you know, like somehow, I mean, you know, something she did on the moon, like instantly gives her knowledge of what will happen if Bob does his experiment. Seems a little weird. In fact, this was like one thing that like Einstein was really not keen on. This was where, related to where he came up with this phrase. Well, it was a German phrase, but the English version of which is spooky action at a distance. And conversely, I mean, also like, you know, if Bob like, you know, measures his qubits, then whatever outcome it gets, he instantly knows what Alice would get if she were to do her measurement. Yeah?
I think he also had a fit in a conference and said, like, God does not play dice.
Yeah, that's another classic
and then
quotation.
someone says, like, don't tell God what to do or something.
Yeah, that's right. I don't know if the God does not play dice was related to this. I mean,
It was just related to...
I think it is. I mean, the fact that, I mean, the laws of quantum mechanics have this probabilistic component to them. Yeah. He's upset about those things. But, you know, it's cool. He did some other good things, so we won't hold it against him. And this might look bad. And maybe actually one particular reason why like Einstein himself may have been like upset is there's like this general causality principle in physics that like information should not be able to be conveyed faster than the speed of light. Okay? And it would seem possibly to you that here like something was conveyed like instantaneously, so definitely faster than the speed of light. I mean in 0 time. You know, as soon as Alice reads out her measurement, she like instantly knows the state of Bob's qubit and what he would get had he measured. So that looks strange, but there are two things to like mollify this situation. First of all, see, Alice does not actually in this scenario convey any information to Bob. Now, perhaps since I'm not defining these terms like information or convey, like it's not clear what this means. But it's not like Alice is able to say, like, I'm going to send a message to Bob, and it's going to be like 1, right? The thing that she came to learn was a random bit. Like it's not something that she herself chose or designed. So that's one mollifying statement. Another mollifying statement is like, arguably, there's absolutely nothing weird about this at all, because there's a classical scenario which is arguably exactly the same, which is following. I mean, it's a probabilistic coin flip scenario. So like imagine Alice and Bob are sitting there together on Earth, and they like write a computer program or like make a machine which flips a fair coin and then puts a second coin the same way up, either heads or tails. So now like it's 50-50 chance that it's heads, or let's call it 0-0, 50-50 chance that it's 1-1. So the Alice and Bob don't look. The machine like does that. And then, the machine covers up the results and passes them over to Alice and Bob. And Alice takes 1 and puts in her, keeps it, but like doesn't look at it. And Bob takes 1, keeps it, and doesn't look at it. Okay, so now it's kind of like mathematically, the situation is like this, only it's like half probability of 0-0, half probability of 1-1. Then Alice can go to the moon or whatever, and they can hang out. And then, like, when Alice is ready, she can say, all right, I'm going to measure this coin. And she like lifts up her hand, and it's 0. Okay, now, she knows for sure immediately that Bob's coin is also 0. And that like whenever he lifts up his hand, there's a 100% chance he'll see 0. Right? And similarly, she lifts up her hand, she sees 1. And she knows instantly that Bob would also see 1 were he to lift up his hand. So you could just say, yeah, what's weird about that? That's fine. So maybe if you compare it to that, then the situation maybe doesn't look that strange. Now, actually, there is a difference between these two scenarios, which implies that the quantum situation actually is stranger, which is that the coins have something property which you might call a local hidden variable. Okay, or they have some local realism property. And what do I mean by that? It's kind of like, when you say, it's 50-50 that the coins are 0-0, 1-1, that's like mathematically modeling your lack of knowledge about the real state of the coins. And like in physical reality, they have some, they either actually both are 0-0 or they both are 1-1. They have some real state that's stored locally in the physical coin object. And it's simply that it's like hidden to Alice and Bob. They don't know it yet. But like there's something that has already been chosen that determines what the outcomes of the experiment are. And that thing is stored physically with the object. So it's local. It just hasn't been revealed yet. Okay? So somehow, right, like the actual real state of the coins is one of these two things. And the 50-50 just models the fact that we don't mathematically have full information.
So can we interpret the quantum phenomenon in the same way?
Good. So the question is, can we interpret the quantum phenomenon in the same way? And Einstein really wanted the answer to be yes. But it turns out the answer is no. So the distinction, or a distinction with the quantum case, is that that's not the situation with the qubits. Like the only true state, like the really real state of the qubits when Alice is on the moon and Bob's on Earth, is this superposition. Like the coin or the qubits or the photons have not yet like decided what state they're in. They're really in this state. Now you could say one thing. You could say like, well, you're telling me that, but like I don't know. I mean, maybe they have. Or like at the time, like in like 1935, when Einstein and Podolsky and Rosen were thinking about this, they're like, well, I don't like that. They're like, I think they thought that these qubits, these photons, like had some like local hidden variable that was going to determine was going to be the explanation for this seemingly instantaneous action. And that we hadn't discovered it yet. Or like the laws of quantum mechanics were not complete. But in like 60s. The person Bell, after whom the Bell state is named, figured out an experiment which proves this scenario absolutely cannot be the case for quantum states. He described an experiment which, if you did it and it came out according to what laws of quantum mechanics would predict, it would like definitively prove that there was like no way like these photons could have some secret hidden state that was explaining the local hidden state that was explaining the outcomes. And then like in the 80s, they did that experiment, and it worked out just as they predicted, and like they've done like better and better, like more sophisticated versions of it since then. So like quantum mechanics won out, and it sort of proves that the qubits do not have this property. And we'll talk about exactly that experiment next lecture. Question?
It was going to be what's that term?
Oh yeah, it's the simplest variant is called this like CHSH game. CHSH stand for the 4 people that invented that variation. Okay, so that's what we'll talk about next lecture. Yep.
So it's more like, I don't maybe relate to the experience because I have no clue what the experience was, but like, instead of like, let's say Alice goes to the moon, and instead of measuring, she can like perform some operation on her qubit, and that should also change the qubit that Bose has. And this kind of this experiment does not coincide with what we have with the coins. You see, if Alice changed the coin, it will not change the coin of the ball.
Good. So in fact, that's what we're going to talk about now.
Okay, good.
Okay. So we're going to up the ante now by doing exactly what was suggested. You can imagine that, well, the way you put it is Alice could do some transformation to her qubit and then measure. Or you could do the same thing, which is kind of the same thing, which is measure her qubit in a different basis. Remember, she can do that. And these are actually kind of the same. You can simulate a measurement in a different basis by like first doing a unitary, measuring in the standard basis, and then doing the opposite of the unitary. And that's going to make it more interesting because like now this is something that Alice has control over. Like here, when she just measures, like she gets a random bit. But like now she can decide to do one thing or the other, measure in this basis or measure in that basis. And as we'll see, it seemingly changes what goes on with Bob's half of the EPR pair. So yeah, let's see what happens. So indeed, what happens if Alice measures in a different basis? And we have one particular favorite basis, so let's just ask about that. What happens if Alice measures her qubit in the plus or minus basis? Okay, remember this is 0, this is 1, and, this is plus, and this is minus. Okay, remember we said that like, well, there's just the rule for like what happens if you measure in a different basis. You can follow that. You can imagine that Alice has like a measuring device that measures in the plus or minus 1 basis. If it's photons, it's like she takes that little 3D glass and turns it 45 degrees, and that's the new measuring device. Or if you don't want, you can sort of simulate this by first doing a unitary that takes the standard basis into the plus or minus basis. That would actually be the Hadamard gate. And then you measure in the standard basis, get a result, and then you undo the Hadamard, which is actually the same as doing a Hadamard, because the Hadamard is actually self-inverse, it turns out. So actually, there's 2 equally good ways to calculate what happens. So let's just calculate both, actually. That'll be it'll be illuminating, maybe. So let's actually do the second way first. So let's simulate this by unitary plus standard measurement. Okay, so in other words, the picture, this is Alice's qubit, this is Bob's qubit. Bob's not going to do anything in this story. Alice is going to simulate measuring in the plus or minus basis by first doing a Hadamard to her qubit, then doing the standard measurement, and then like kind of, rotating things back. Okay, this is, by the way, H is equal to H inverse. Remember, the H is that operation which reflects in this axis. Okay, so it takes plus to 0, and it takes 1, and it takes 1 to minus. It's a reflection, so it's its own inverse. Okay, so let's work it out here. So what's the state here? This is the starting state, the Bell state. So what's the state here? We just do a Hadamard to the first qubit. So the state here is 1 over root 2, Hadamard applied to 0, tensored with 0. plus 1 over root 2, Hadamard applied to 1, tensored with 1. Okay, here we applied the rule from last time about like what happens if you do a unitary to 1 qubit in a joint 2-qubit system. Okay, and now we just do algebra. So this is 1 over root 2, like I say, plus tensored with 0, plus 1 over root 2, minus tensored with 1. And let me just expand out the definition of plus, right? It's the thing 1 over root 2, 0 plus 1 over root 2, 1. Right, this is 1 over root 2, 0 plus 1 over root 2, 1. And I guess this is 1 over root 2, 0 minus 1 over root 2, 1. Okay, so in order to save space, imagine like I had written the definition of plus, which is this here, and then I expanded it out by distributivity. Then what would I get? I'm just skipping a step here. I would get 1/2, 0, 0 plus 1/2, 1, 0. Right? And if I did the same thing here, I placed minus with its definition and expanded out, I get plus 1/2, 0, 1 minus 1/2, 1, 1. Okay? So stop me if I make a mistake. Okay, so then that got us up to this point. Now we apply our, the rule that we have now learned for how things behave if you measure 1 out of 2 qubits. Okay, so now Alice measures. Okay, so with probability, I'll just say this, the probability that she measures 0 is we square the amplitudes associated to the basis states that have a 0 here. So we get a half squared plus a half squared, which is a half. So there's a 50% chance she gets a 0. And then the state collapses to this unentangled state, 0, tensored with. What's left? She picks up this and this. And we have to normalize these two parts by dividing by square root of a half. So let me just write it here. It'll be 1 over root 2, 0 plus 1 over root 2, 1. Right? This expression is what you get if you pick up these two underlined parts and normalize them to be a state. Which, by the way, is 0 tensored with plus. Okay. So there's a 50% chance in this experiment that she measures 0, and then the state changes to 0 tensored with plus. And by the way, since what she's trying to do here, this was all in an effort to like simulate a measurement in the plus or minus basis, then when she gets, when this thing pops out like 0, she really says, oh yeah, that means like plus. Right? And then remember, what is the last thing she does when she, in this case, Hadamard on the first qubit? So the thing she does is sort of rotate things back. Well, that takes this 0 to a plus. The final state is actually plus tensored with plus. Okay, and that's consistent with like she pretended that the outcome was plus, and like now after fixing up, undoing the rotation, it really was plus. And when that happens, Bob's state is also plus. Okay, that's half the cases. I'm going to leave the other half of the cases as an exercise to you. But I'll say what happens as an exercise. Okay, we know with 50% probability she reads out a half. Which she interprets as minus. And finally, the final state in this case turns out to be minus tensored with minus. Is that okay? So actually something kind of perhaps even more interesting has happened. Look what's happened here. When Alice decides to measure in the plus or minus basis, and we've analyzed it by doing this, she again gets plus or minus as her readout with 50-50 chance. And Bob's state like snaps to either plus or minus, whichever one she read out. Which is similar to before with the zeros and ones, but a little bit even more interesting now. And let's do the analysis the other way. The other way, if you want to understand what happens when you measure a joint qubit state in a non-standard basis, what you just need to do is take this state and express it, re-express it as a linear combination in such a way that the first component is plus or minus. So just like express the first qubit in the plus or minus basis, and then use like the usual rule. I'll explain what I mean here. So, right, so let's go back to the beginning where the EPR pair that they share is 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. And since I want to measure the first qubit in the plus or minus basis, I just say to myself, let me rewrite it so that the first kind of component is expressed in the plus or minus basis. So like, I'll first do that for 0, 0. I'll try to re-express the first part in the plus or minus basis. And then I'll also do it for 1, 1, and I'll add them up. OK, so I'll just do that like this. This is 0 tensored with 0. And then how do I write 0 in the plus or minus basis? I just erased the picture I need. 0, 1, plus, minus. So you see 0 is an equal superposition of plus and minus. OK, so you could just work this out. This is 1 over root 2 plus 1 over root 2 minus. OK, tensored with 0. OK, so this is 1 over root 2 plus 0, if you will, plus 1 over root 2 minus 0. OK, and let me also re-express 1, 1 like this. So this is 1 tensored with 1. OK, and 1 is actually plus take away, ket minus. OK, so you can check for yourself. This is 1 over root 2 plus minus 1 over root 2 minus, tensored with 1. Just 1 over root 2 plus 1 minus 1 over root 2 minus 1. OK. So just continuing, now I know what 0, 0 is, it's this. Now I know what 1, 1 is, it's this. So I'm just going to add up this with coefficient 1 over root 2, and this with coefficient 1 over root 2. OK, so therefore this equals, so let's see, I'll get a half plus 0 plus a half minus 0 plus a half plus 1 minus a half minus 1. OK, again, these two states should be equal. I'm just really doing a bunch of algebra. And let me factor this, because I'm really kind of interested in like the component that has plus at the beginning versus the component that has minus at the beginning. So this is plus tensored with half 0 plus half 1 plus minus tensored with half 0 minus half 1. And this is basically the ket plus state, right? Times 1 over root 2. And this is basically the ket minus state times 1 over root 2. So this equals 1 over root 2 plus 1 over root 2 minus minus. So what we've seen by algebra is that this state, this vector, is literally the same thing as this vector. Okay, they're just algebraically equal, which looks surprising maybe at first, but it's a fact. I mean, it's a little tricky for your intuition, right? This is all taking place in 4 dimensions. So there's some kind of like 4-dimensional basis. I only have 3 fingers, but some kind of 4-dimensional basis. And you know, let's say this is the standard basis. And this is like some certain linear combination of 2 of the basis vectors. So like maybe it's like this one. It's like this one. Like maybe it's a combination of this one and this one. So like this is terrible, but like, yeah, I can't even do it. It's like, yeah. OK, it's like some vector coming out. And then this is also a basis, plus plus, minus minus, plus minus, and minus plus. It's also some different 4-dimensional basis that's like orthogonal to it somehow. And like, it's just saying that like that special vector that we care about, the EPR pair, yeah, it's an equal superposition of these 2 basis vectors. It's also like some equal superposition of 2 other basis vectors in the plus or minus world. That was the best I could do there. OK. But now, like once we've finally written it in this way, you know, what happens when like A measures in the plus or minus basis? It's very vividly clear. You know, she puts it through her 45-degree 3D glasses polarizing filter. What do? Well, she either reads out plus, and according to our partial measurement rules, what is that? You take all the components that have a plus in the first position and square their amplitudes. So it's 1/√2 squared, which is a half, as we saw before. And in this case, the state, you know, collapses to plus tensored with plus. Okay, else, you know, she reads minus on her measuring device, and state becomes minus tensored with minus. And as we saw, we just did the same calculation 2 different ways. And we saw this kind of cool fact, which is she sees the 2 outcomes plus or minus with equal probability. And then Bob's state snaps to exactly her state. OK, so again, like she now knows, let's say she does it, and her readout device says plus. She now knows for sure that if Bob is going to measure his state in the plus or minus basis, there's a 100% chance he'll get plus. And you know, Bob measures it in other basis. Sorry, if she measures and gets a minus, then she knows for sure instantly Bob's state is minus. And if he were to measure in the plus or minus basis, there's a 100% chance he'd read minus. And this actually is, I think, more, you know, knowing this is like more spooky or more interesting than before, because now Alice, you might think, maybe now Alice really can convey some information to Bob. Maybe she can convey one of 2 different possibilities to Bob, because now Alice has like some choice, right? She has some volition. She can either measure her qubit in the 0, 1 basis, and then Bob's state will like snap to some 0, 1 value that she knows. Or she can choose to measure in the plus or minus basis, and then Bob's state will collapse to some plus or minus 1 state that she knows. And like it would seem that like in these 2 possibilities, Bob's state of the world is quite different. So like now, Bob can maybe tell the difference between his state. You know, it's either in the 0, 1 basis or the plus or minus basis. And maybe in that way, she can convey some information to Bob. So let me even try to write that. So, you know, Alice can do some things. She, you know, her choice 1, she can like measure in the standard basis. And then what's the situation? You know, she doesn't really care per se what she gets, but now when she does that, there's a 50% chance that Bob's qubit is 0. And there's a 50% chance that Bob's qubit is 1. You saw that, right? Or state 2, or sorry, choice 2, she can measure in the plus or minus basis. And as we've just seen, when that happens, there's a 50% chance Bob's qubit collapses to plus, and there's a 50% chance Bob's qubit collapses to minus. This looks very different. Let me call this situation row 1. And let me call this situation row 2. Turns out that, well, not turns out, but here, row 1 is a mixed state. Remember we talked a little bit about mixed states, right? It's a probability distribution over quantum states. And row 2 is also a mixed state. It's a probability distribution over quantum states. And they look very different. I mean, I did not use the same words here as I used here. They look very different. And so it would seem that if Bob can just now take what he's got and tell the difference, is he in case row 1 or case row 2, then he can learn what choice Alice made. In fact, even if he can only come up with a good guess about whether he's in case row 1 or case row 2, he'll have come up with a good guess about what choice Alice made. And this all could have happened instantaneously, faster than the speed of light, which looks very nerve-wracking. But the resolution is the following. There's no physical experiment that Bob can do that will allow him to tell the difference between this state, this mixed state, and this mixed state. And again, you'll actually look at this on the homework. But it turns out that if you're let's imagine Bob rotates his qubit and then measures it in this basis, or I don't know, does this, measure in this basis, you will find that the outcomes in the row 1 case are identical to the outcomes in the row 2 case. And if you want to quickly think about it, just imagine what would happen if Bob measured in the classical basis. Well, here in the standard basis, here he'd see 0 with probability 50% and 1 with probability 50%. And also here, you have to think about it, but if you run through a little calculation, you'll see that he'll see 0 with probability 50% and 1 with probability 50%. And no matter what you can think of, Bob might do, he'll get the same outcome here or here. So in fact, he cannot tell the difference between these. These are in fact identical mixed states. And this is the reason why Alice cannot use this trick to convey information to Bob. Let's stop there. But now I'll also take your question. I mean, if you need to go.
So, is there a reason